Okay, so last class we were talking about classifying volcanic eruptions. I guess before I get there, your exams, I know you guys are thinking about them. I've started them. I don't have them done. I'll have them for you next week. There's a lot to read. You guys wrote a lot. What I've read so far is good. All right, so last class we were talking about classifying volcanic eruptions, and we went into a couple different ways. Volcanic eruptions are, it's a series of events, and sometimes volcanoes follow a well-established series of events so that we can classify other eruptions according to them. But a lot of times volcanoes fall outside the norm. So it makes it really difficult to classify them based on observations of active volcanoes. And that's what we're doing here. We're looking at famous volcanoes that have erupted during the scientific era, looking for patterns in those eruptions, and then trying to apply them to other volcanoes so that we have a working vocabulary on how these things erupt, some similarities, some differences. So the first type eruption that we talked about last class was the Hawaiian type. Hawaiian types typically start out as a curtain of fire as lava erupts through a segment of a rift zone. Because that's not the most thermally efficient way for lava to erupt, and if you think about a tabular feature like a curtain of fire in a rift zone, you have a lot of surface area where it can lose heat. That's not efficient. So what tends to happen is as the eruption proceeds, the curtain of fire shrinks down to a single focus or a single vent. Then the eruption columns get much higher, followed by lots of lava flow emplacement. So that's kind of the typical Hawaiian. Start with a curtain of fire, localized down to a vent. Any explosive activity tends to be pretty low fountains, forming things like cinder cones and spatter cones, but then lots of lava flows come out after. The second type is kind of the next notch up in intensity. Hawaiian eruptions are powerful and impressive, but as we go through the list, they get more powerful. And I think you could argue more deadly as well. So Strombolian is kind of our next step up on the intensity scale as well. Strombolian eruptions have higher, more energetic columns. They don't tend to be sustained like you see with the Hawaiian eruptions, where you get hours and hours and sometimes days and days of curtain of fire and then fire fountain activity. These tend to be discrete, frequent blasts. Some of them last minutes. They can last up to an hour. Lava flows, unlike with Hawaii type, are very rare. These just tend to be blasts of material that then accumulate near the vent and form these nice cinder cones that you see here. They tend to be basaltic to basaltic andesite in composition. These are named for the volcano Stromboli, which is an island off the west coast of the Italian mainland. You can go there, you can take a boat, you can climb up, you can get up above the vent, watch it blow up beneath you. Your ears can ring. You can feel the ground shake. I'll show you a video here in a minute. It's pretty impressive. Again, these tend to form cones as ash and cinders pile up. And as I said, Stromboli, Italy is the type locale, but this is a fairly common type of eruption. Many of the Icelandic volcanoes show Strombolian activity, especially as the eruption wanes in Iceland. And I mention this because, again, it's important to point out that Hawaiian-type eruptions are not confined to Hawaii. Strombolian eruptions are not confined to Stromboli. And in fact, you can get these types of activity at other volcanoes, and even Hawaii and Stromboli themselves can show other types of eruptive behavior as well. So again, Hawaiian type, curtain of fire, localized down to a vent, which makes a higher fountain. Eventually the fountain wanes in size and starts feeding extensive lava flows. Strombolian eruptions are discrete blasts that produce lots of cinders that pile up near the vent. They're pretty powerful. You'd be impressed. I've got some, this isn't the best video in the world. Let's see what I got, but it is a video. I don't know if the sound is on this. So you can see the Mediterranean in the background, so it's an island. These are very small at first, some get a little bigger, but discrete blast, throws up material, falls back down, you can see the cone forming. This video shows some at night, which are, it's a different perspective. I'll just let this run for a minute and watch. You can get small shock waves. You could tell there at the beginning it shook pretty bad, and it can hurt your ears. That's more typical there, where you can see the power. But these blasts are lasting seconds. You can get bigger ones, but this is pretty common for Stromboli.
You said they don't commonly have lava?
No, you just blast these cinders out and they just pile up all the time. It's really rare for Stromboli to have a lava flow. The material's just a little too gaseous, so it's constantly exploding, ripping it apart. Yeah, it's what happens when you get a little more gas rich or a little more viscous, because basaltic andesite was one of the magma types. That tends to be viscous enough that lava flows don't flow easy. Palaean eruptions. These are scary. These kill people. This is named for Mount Pelée, which we talked about a little earlier this semester. Mount Pelée is on the island of Martinique, erupted in the early 1900s, wiped out an entire town.
Isn't that the one where the guy survived in the...
Yep. Drunk naked dude was one of the lone survivors. Palaean eruptions are characterized by pyroclastic flows that come out of a volcano that has a lava dome. We'll spend some time in a week or two talking about lava domes. Again, the pyroclastic flows are basically avalanches of material that descend down the volcano at rapid speeds. Typically on the order of 100 miles an hour. Can be several hundred miles an hour. Sometimes they travel a few hundred meters. Sometimes they can travel tens of kilometers. But they are always associated with lava domes. That's really the key, is that they're characterized by pyroclastic flows from volcanoes that have active lava domes. And lava domes tend to form on volcanoes that typically are erupting silicic magma. Andesites, dacites, rhyolites. So these really viscous, pasty lava flows that are too viscous to flow very far, so they mound up on top of the volcano. They become oversteepened, and chunks of them can slip away. If the chunk that slips away is small, it'll break up into a small pyroclastic flow. I'll show you Arenal volcano here in a second. These are really tiny pyroclastic flows. And then, but some of them can be bigger. If you get a big chunk that comes off, it can be a really impressive lava or a pyroclastic flow. I don't have any video of it, but I have a photo of one that I took in Russia a few years ago. Scared the shit out of me. So again, formed by dome collapse, or an explosion that comes out sideways beneath an active lava dome. And there's some evidence that lava domes can have gas-rich areas that can simply explode from within. There's a really interesting volcano in Guatemala called Santiaguito, and it has a lava dome. But every once in a while, a lava flow will come out of the lava dome, which seems really weird, and travel down the volcano several kilometers, and then the very end of the lava flow explodes and produces a pyroclastic flow, which is kind of scary because the lava flow basically brings the material close to towns, and then the pyroclastic flow gets to some of these villages on the side of Santiaguito and wipes it out. And for a lot of years, you just didn't know how the inside of a lava flow could explode. But now there's been some papers that have come out that have some ideas on how that might happen. We'll talk about that in a few weeks. But the bottom line is pyroclastic flows associated with active lava domes.
And this is a debris flow.
It is an avalanche. So another term for it is what we call a block and ash flow. So the lava, most of these are caused by dome collapse. You know, maybe the lava flow can explode, and maybe you can get a eruption that comes out at the base of the lava dome, but mostly it's from lava domes collapsing. So basically it's hot rock that sloughs off and starts rolling down the hill and breaks up into smaller and smaller pieces. And then those tumbling blocks collide together and produce lots of ash. So really what you have is a two-part avalanche. You have a basal block flow where it's just the blocks rolling down and they're hot. And then on top of it is what we call a surge. And it's kind of a dilute, ashy cloud that moves down on top of the pyroclastic flow. And what's interesting is the pyroclastic flow, the base, the blocky part, will follow the stream valleys. But the surge, because it's dilute, if you have a pyroclastic flow and surge that's going downhill, and let's say the valley hooks a left turn, the dense avalanche part will follow the valley, but the dilute surge cloud might just keep going straight and hop hills and just go over topography. And there's been lots of examples of the surge detaching from the avalanche and just doing its own thing and killing people. It happened at Montserrat a lot. It would just bounce over the top of these mountains and just keep going down. Or what it'll do sometimes, if it hits the ocean, the avalanche buries itself into the ocean water, but the surge will just scoot along the top of the water and go out to sea, and it's engulfed ships and things. So they're interesting. They're weird. I have a video of that happening. I'll see if I can pull it up after the break and we can watch it. So, okay, so here I'm going to show a video of some really pretty crummy block and ash flows from Mount Arenal in Costa Rica. There's an active lava dome up at the top. So silicic lava is piling up there. When it gets oversteepened, little pieces of it collapse. Sometimes bigger pieces collapse and it goes farther, but that whole area off to the left is just blocks that have fallen off the dome. And then you can see the ash go with it. So I'll just let this run. So they missed that one, but you can see the fresh hot rock that's come down. That's the basal avalanche. And that whole slope is covered with that material. There's a few blocks coming down. That's really bad. Weak. So there's one starting up on the top, so a big chunk of the dome just collapsed. And it'll roll down, all the blocks will collide into one another. It'll make that elutriating ash that you see go up. So these are tiny. You see the ash cloud, that's called the surge. It's dilute, but underneath it is a rolling bunch of blocks, and you'll see them poke out the front of the cloud every once in a while. You see right there, that's a pretty good view. So even though it's a bunch of tumbling blocks and ash, as a unit it kind of behaves like a flow. And geologists model it using fluid dynamic equations. So that's a little block and ash flow. Now if that hit you, even that little thing, you would die instantly. Combination of getting pummeled to death and vaporized, because that stuff is over 1,000 degrees C. I don't know if there's any, but let's try this. So if you look at the very front, you can see the individual block sometimes gets spit out in front of it. You can see it's moving along pretty well. You're not going to outrun that. You don't want to get hit by that rock. But basically inside that cloud, there's thousands of those blocks just colliding and rolling, and when they collide, they make fine ash that gets carried up on the hot air. The bigger they are, the faster they tend to move. Okay. All right, those are pretty small. I think I have a... There's one a little bigger. That's the one I took a photo of. It's Kizimin volcano in Kamchatka. So that thing traveled, that's actually a couple of miles. And it traveled a couple of miles in about 15 seconds. So they're fast, they're powerful. You get caught inside it, one of them, you are done. Okay, so that was Palean. So Palean, pyroclastic flows, typically from the collapse of a lava dome, sometimes from beneath a lava dome and sometimes from within a lava dome, but mostly just from collapse. Okay, the next type eruption is from Volcano, Italy, and they're called Vulcanian eruptions. These are big vertical blasts, usually several thousand feet. They typically come out at regular intervals, and they come out fast. A lot of times they're ejected at supersonic speeds and have really pronounced shock waves that can knock you on the ground, actually. And when I say tall columns, we're talking miles tall. They sort of resemble a strombolian, where it's a discrete blast. These are just much bigger. Now, sometimes you get a few kind of in the middle ground. It's hard to know, well, are they strombolian or are they Vulcanian? A couple of ones I'm going to show today are kind of in that ballpark where it's, well, you could argue about it. Volcanic eruptions can happen with lots of different magma types. Can happen with basalt if it's particularly gas rich, or especially if basaltic magma is mixing with a certain amount of groundwater. Typically, andesites are the ones that produce probably the most pronounced Vulcanian eruptions, but it's not limited to a certain magma type. The columns tend to be pretty dense, lots of ash. And in fact, if the ash is dense enough, what will happen is the volcano will throw up this dense column of ash, but then gravity drags it back down in the form of a kind of an ashy pyroclastic flow. So the column can actually collapse and then descend the sides of the volcano as a fast-moving, dilute pyroclastic flow. Because it's so powerful, these types of eruptions have been known to throw really large blocks a fair distance. During a Vulcanian eruption, you would not be safe anywhere on the cone of the volcano. That's certainly within range of throwing big blocks, and probably for a mile to several miles off the cone itself. Because remember, these columns are going up 6 miles or more, so 30,000 feet. It's believed that the gas for a lot of these is actually groundwater getting into the system. So the clouds a lot of times are really dark when the ash is mixing with some of the steam. That comes from groundwater interacting with the magma and flashing to gas. So it's pretty common to see these tall columns really dark from the condensation of steam onto the ash as it's erupted. But there's some new material as well. So we call these phreatomagmatic eruptions. Phreato from the interaction of groundwater along with real magma, so it's a mixture of both. So you'll see really dark parts of the column, really light parts of the column. Really high eruption speeds and really strong shock waves. So I have a couple of volcanoes queued up here. One is Sakurajima. This is a volcano in Japan that only sits a few miles from a really large town, Kagoshima. The people who live in Kagoshima routinely walk around with hard hats on. Kids walk to school with hard hats. They have volcano drills every week because sometimes the explosions are big enough to throw bombs from the volcano into town. These land in town. What's that? It depends how big the block is. If the block is this big, you know, your head won't split open, but your neck will snap. You know, it's one of those things. But yeah, but there, a lot of times the rocks are maybe this big, and you definitely want a hard hat on for that. But yeah, I mean, if you have a basketball-sized rock falling out of the sky and it hits you when you're wearing a hard hat, it'll be of minimal help. So let's see what we got here. So this is Sakurajima, and then Santiaguito, the one I have after it, is a volcano in Guatemala that I talked about earlier that sometimes have lava flows that explode. So this is just sort of queued up on the vent of Sakurajima. You can see the dark cloud. So this goes on all the time. Boom, boom, boom. Sometimes a few times a day, sometimes 100 times a day. And you can see on the flanks there all the rocks coming down. See how dark some parts of the cloud are? It's believed water is soaking into the magma system and flashing the steam and driving this. This video does a poor job of showing the size of the column, but it's impressive. It'd be several miles tall. You can see it's much bigger scale than the Strombolian one I was showing earlier. And you can see it sustains much longer as well. Ash falling out of the cloud to the right. And then this is just from a couple years ago. Some guys from Liverpool decided to fly a drone over Santiaguito, which is kind of cool. I've climbed. So Santiaguito is a lava dome that sits on the side of another volcano called Santa Maria. Santa Maria is this beautiful 13,000 foot cone in Guatemala. It erupted in the early 1900s and blew the side out of the volcano, but left the peak. So it was an eruption that was really similar to Mount St. Helens, except it left the peak behind, but then a big amphitheater-like crater on the side. Then 20 years later, so this thing just sat there with this big gaping hole in the side of the volcano for 20 years, no activity, and then after 20 years, suddenly a lava dome started forming. And it's still erupting today. The lava dome will hit its 100th year anniversary in 2 years. So it's been erupting steadily, and the lava dome is huge. It's enormous. But it has a little area that commonly has volcanic eruptions coming from it. So what's really cool, though, is you can climb to the peak and then look down on the lava flow and watch it blow up. I've done this several times. It's awesome. You climb it in the middle of the night so you can be up there for sunrise, and then you watch the volcano erupt, and it sends the ash column up, and then it blows over the top of you and drops ash and little rocks and stuff on you. For a volcanologist, it's super cool. But now with drones, it's even better because now you can fly the drone right over the vent. And I love this video because that's what somebody did. So, but this is just a tiny part of the lava dome right here. It's just the vent area. The lava dome goes for miles. It's enormous. But this is the part of the lava dome that blows up and has volcanic eruptions. So I'm just going to let it go because the drone goes over right as it erupts. See the dark material? Okay, so you just get a sense for kind of how powerful that thing can be. Let's see what else we got here. All right, those were those two videos. All right, a fifth type. So there's 7 or 8 types of eruptions that we'll talk about, type eruptions. This one's Surtsian, for the island of Surtsey that formed off the coast of Iceland back, I think, in the 1960s. I'm not sure of the date. Surtsian eruptions are characterized by eruption through water. Explosive eruptions into the air, but through water. It can be the ocean, but it can be lakes as well. These are really violent eruptions. Lots of water present, so the eruption columns tend to be really dark because of all the water. The deposits it leaves behind are tuff cones and tuff rings. Tuff is the term for broken up pieces of volcanic rock formed during a volcanic explosion. Because these are so violent, the ash tends to be super fine. Really, really fine ash, almost sand size. The eruptions are so violent and there's so many collisions that the stuff just fragments down to the smallest pieces. Again, it may occur in oceans or lakes. I'll show you a video of Surtsey, which popped up in the Atlantic Ocean off the coast of Iceland. There's another volcano in the Philippines called Taal Eruption, or Taal Volcano. It's an island that has a caldera, and then within the caldera, another island formed. And then that island blew a crater that has a lake in it. And in the middle of the lake, you get lots of Surtsian eruptions, so you get a tuff cone. So you get an island in a lake, in an island in a caldera, and an island in the Pacific Ocean. It's like multiple generations of water, islands, eruptions. So it's kind of a neat volcano. So 1963, the birth of the island of Surtsey. This was during the age of video, so there's actually video of this thing forming. It's old, it's low resolution, but it's still pretty cool. I'll show it to you. So the formation of Surtsey itself Started along a shallow part of the mid-Atlantic rift, about 500 feet below sea level. The Vestmenier submarine system, it's part of the mid-Atlantic ridge. So there were these undersea eruptions for a while, and then some of the explosions were so powerful that some of the eruption columns would come through the ocean surface, and then eventually enough material was deposited that a little island poked out late in 1963. So again, really powerful explosions, really finely fragmented material that made these little tuff rings and tuff cones, and eventually an island. So I've got just a minute or two video coming up. It's going to show some of the eruptions from Surtsey, so you'll see this material blasting through the sea. And then there's another eruption that it shows, which is Heimaey, which is on Iceland itself, but it was right near one of their major fishing ports. And just in the middle of the night, a volcano started erupting right on the edge of this town and completely engulfed the town within a couple of days. Covered all the buildings, all the homes, but the big problem is that it started producing a lava flow that started creeping across the harbor, and it actually threatened to completely seal off the harbor, and this is a fishing village. So the fishermen and all the people living there didn't want this to happen, so they all had been evacuated, but they all came back in the middle of the eruption and set up, I think, something like 16 miles of pipe and pumped seawater onto the lava flow to get it to stop. And there's always been disagreement for the last 50, 60 years about whether the lava flow stopped, and it actually did before it closed off the harbor, whether the water that they squirted on it had any effect at all, or whether it just stopped on its own. But I think I have a couple-minute video here where you'll see both of these eruptions. So Surtsey, with its typical Surtsean type of eruption through the ocean, and then Heimaey, which has lots of strombolian. You'll see lots of strombolian blasts from it. So let's see what we got. So again, here we go.
The eruption lasts for 4 years. On the island of Heimaey.
Okay, let me go back to the beginning here, since I didn't have the sound on. So at the very beginning, we'll see some of Surtsey blasting through the ocean. It doesn't have great video, it doesn't last long. But then it goes into Heimaey, and you'll see that Heimaey, even though it's in Iceland, started as a Hawaiian-type eruption. You will see a big curtain of fire, then it localizes down to a vent, and then you get lots of strombolian blasts. So one eruption can actually take on several eruption types.
1963. A new volcano emerges out of the sea to the south of Iceland. Surtsey. The eruption lasts for 4 years.
So pretty powerful, very fine fragments. There's your curtain of fire.
1973. On the island of Heimaey, 20 kilometers away, a fountain of lava erupts 150 meters from the town of Vestmenier. The city is transformed into a kind of Nordic Pompeii. Hundreds of houses are buried in the ash and scoria, or crushed by lava flows. In the crater, the eruptions are particularly violent as lava meets seawater.
Got to get the good photo.
A few months later, a new volcano stands above the town. Eldfell, the mountain of fire.
Okay. Okay, so in that last eruption, you saw some Hawaiian type, saw some Surtsey type, and then it actually had some Strombolian going on too. So it had all these different types of activity as that volcano formed. Let's see, that was that. All right, any questions? All right, let's do this one and then we'll take a break. So Plinian. Plinian eruptions were named for the Great Vesuvius eruption in AD 79. This eruption was witnessed by Pliny the Younger, who was a philosopher, and a disciple of his uncle, Pliny the Elder, who was actually killed during this eruption. So in respect for the Plinies, we call it Plinian eruptions. These are scary eruptions. Really high columns, up into the stratosphere. So columns that are 20 to 40 miles tall. So it'll eject ash up into the upper parts of the atmosphere, and then it gets carried on the jet stream, typically around the world. These are global events. And they don't happen often. Every few years to a decade. And they're sustained. Everything that we've seen up to this point with the blast, they've been discrete blasts that just last a couple of minutes. A Plinian eruption will last hours to days. There's even reports that Santorini, a volcano in the Mediterranean, which erupted about 1,000 years ago, had a Plinian eruption that lasted 29 days. It evacuated so much magma from the chamber that the entire volcano collapsed into the Mediterranean. It was an island in the Mediterranean, and it's actually what most archaeologists believe is the basis for the lost city of Atlantis. It's believed that there was an island, had several communities on the coast. This volcano in the middle of the island erupted for a month, and then the whole island basically collapsed into the ocean, just leaving a few fragments. And they've taken submersibles now to Santorini and looked at some of these blocks that sunk into the Mediterranean, and they're finding cities that have been under the ocean now for 1,000 years. So it might be the origin for the lost city of Atlantis. So these things, powerful, sustained. You've heard of Pompeii and Herculaneum. What happened there was these Plinian columns are so tall, so laden with material that sometimes gravity pulls the column back down, and all of that material then descends the flank of the volcano as huge pyroclastic flows and surges. Pompeii was buried under huge pyroclastic flows. If you go there and look at the actual rock that's encasing the city that was entombed by it, you'll see big blocks and ash and pieces of pumice. Herculaneum met a different fate. It was also inundated with volcanic material, but it was just the dilute surge, the fine-grained material that came down. People were waiting to be evacuated by boats at Herculaneum when surges came down and entombed them. And I don't know if you've seen the plaster casts of people and dogs that were waiting to be evacuated. The surge material was so dilute but hot that it covered all the people. Actually, they were sleeping, waiting for boats to show up. Big surge came down, left a deposit 3 or 4 feet thick, completely covering the people that were waiting to be evacuated. The material was so hot that it vaporized all of them. And then, I don't know who decided to do it, but people who were excavating the area found these crazy voids in the surge deposit, poured plaster in it, and they actually captured people in kind of their final death poses. I'll pull up some photos for after break and you can take a look at them, but yeah, pretty gruesome actually. Typically these Plinian eruptions form with silicic material, so andesite, dacite, and rhyolite. The ash and pumice can be dispersed over huge areas, continents, and then the lightest material gets up into the stratosphere and is carried around the world. As I mentioned earlier, the reason it's called Plinian is because this entire eruption was observed and described by Pliny the Younger, who lost his uncle during the eruption. So there's the plaster casts. Some of these are from Herculaneum. If you look on the internet, some are from Pompeii, but both areas were covered by pyroclastic material and entombed people who were vaporized, and then someone poured plaster into the rock to where the people were, and this is what they came up with. There were dogs and people and just a real gruesome scene. So these Plinian eruptions erupt a lot of material. The columns typically collapse to form large pyroclastic flows and sheets. And these pyroclastic flows and sheets can be very thick, hundreds of feet thick to thousands of feet thick. And the material is so hot that sometimes all the hot, loose ash that comes down as a pyroclastic flow and deposits in the valleys, it's so hot that they'll fuse back together. And this is called a welded tuff. Sometimes it's just pumice that falls out of the air. So you can get large pumice deposits. That loose material can mix with water if there is any in the area. This is one of the big problems they had after the Mount Pinatubo eruption back in 1991. When Pinatubo erupted, it produced Plinian columns for several days. That material fell back to Earth right during the rainy season and then was picked up by all the monsoon rains and formed massive mud flows. All right, I'll give you a break and I'll queue up some more videos and see what I can find for you.